Alright, in class we've been examining the nature of the absolute value function. It seemed like every time we have a graph of an absolute value function, we seem to get two rays. One ray has a slope of 1, and the other ray has a slope of -1. What I've discovered, and which is what we've been exploring, is the graph of the absolute value function can be moved all over the plane just by changing the equation a little bit. And what we explored before was this looks a lot like point-slope formula in as much as we can walk it home. So, for the first example, it appears as though the function has shifted down 5. And that makes the vertex now, instead of 0, 0, the origin, it's now 0, -5. This means that my equation is going to be the absolute value of x minus 0 plus -5. In other words, this equation says take the absolute value function, which used to exist here at the origin, and this minus 5 says take all of the y values and move them down by 5. So it's not just the vertex. Every other one of these points is moving as well. All the solutions are going to be 5 lower, which is why the graph appears to have shifted down. The result is a graph whose composite of two different linear functions, one who has a slope of -1, or positive 1, and the other has a slope of -1. The y-intercept of each line is -5, which means the equation for the first line, the one with the decreasing slope, is going to have -1x minus 5. The second line, same y-intercept but a positive slope, x minus 5. Which basically means the absolute value function is half x minus 5 and the other half -x minus 5, as shown on the graph. Looking at the related graph, this function appears as though, or this graph appears as though, the original absolute value function was shifted to the left 5. Using the walk-at-home method, or the point-slope formula, sort of, we can see that we get x minus the -5. So whatever the x is, we're going to subtract it, and in this case that causes y equals x plus 5. Notice again, it appears as though the graph of the original function has shifted entirely to the left. All of the solutions to the original equation have all shifted left of the origin, even though this says x plus 5. As you can see, when x is -5, -5 plus 5 equals 0, which is the solution represented by the vertex. Once again, we get two half lines, which is really the absolute value function is actually the composite of two half lines, one of whom has a slope or y-intercept of 5 and a slope of 1, producing that equation. The other has a slope of -1, and I just have to explore a little bit and see that if I extended this line, it would have a y-intercept of -5. So this equation has a slope of -1, y-intercept of -5. So this absolute value function is essentially comprised of one half of the line x plus 5 and the other half of the line -x minus 5. Following the same patterns, we could recognize that we can shift not only just one direction, we can shift in two directions, which is going to be the next boy band, I'm sure. Anyway, we can observe, since the vertex is 3, 4, that the equation is going to be x minus 3, we moved right 3 from center, plus 4, we moved up 4 from center, and that's demonstrated by this transformation. All of the solutions to the equation, not just the vertex, have been shifted over 3 and up 4. That produces two equations. The line y equals x plus 1. I got plus 1 by extending the line back to the y-axis. The other one is y equals -x plus 7, which essentially means if we take the equation, remove the absolute values entirely, we get the first line. Boom. Looking over here, we take the equation. Not only do we remove the absolute values, but we take the opposite of everything inside the absolute value. We get -x plus 3 plus 4. Notice that that produces the equation of the second line. So, looking at this again, here the new vertex is -4, 3, which means the graph is shifted to the right 4, or left 4, sorry, and up 3 from the origin. So here is the simplified form. We moved left 4, up 3. This says positive 4, which means we moved left 4, up 3, producing the line y equals x. Here's the y-intercept at 7, x plus 7. And here's the line y equals negative x. Extend the line downward to see negative 1 is the y-intercept. So this is half of this line. Notice again, what I've done is I've removed the absolute values and done nothing to the inside, producing y equals x plus 7, which is the right half line, or ray. For the second equation, all I have to do is take the opposite of what's inside the absolute value, that's negative x minus 4, add 3. That produces negative x minus 1. So, once again, these match. Going through the same process with less speech this time, vertex, right 3, up or down 4, vertex, left 5, down 2, simplified form. We can see y equals x minus 7, which if you take the equation, remove the absolute value, you get y equals x minus 7, the first half line, and y equals negative x minus 1, here's the y-intercept. And if we remove the absolute value but negate the insides, we get negative x minus 1. Same thing down here, find the y-intercepts, mark the lines, and express accordingly. That went by really fast. I recommend, if you would like to take the notes on this video, pause at this moment and you can write down some of these notes. Continuing now, these functions are looking like absolute value functions, but it appears as though the slopes of these functions have changed. And so what I'm going to do is recognize that I can combine the slope, like we use with linear functions, with an absolute value, and that's going to affect the steepness of both rays. One will have a positive slope, and the other will be the opposite slope, which will be just as steep in the opposite direction. Here's what I know. From this point on the graph, 1, when x is 1, y is 3.5. What I can do then is substitute 1 and 3.5 into this function format, and that means that a has to be equal to 3.5. In other words, I have a new function that shows the slope 3.5 times the absolute value of x, which produces the graph shown. Notice again we get two half lines of two rays. This one has the negative slope with the 0 y-intercept, and this one has the positive slope with the 0 y-intercept. And the slope is rise over run, change in y over change in x. We go up 3.5 over 1. So, the one equation is generated by removing the absolute values entirely. The second equation is generated by taking the opposite of whatever is inside the absolute value and multiplied by the coefficient. Following the same format below, without talking, you can follow along. Pause if you need to. Now here we see that the absolute value graphs have become upside down. They've been negated essentially. They used to have all that positivity. All the y values were positive all the time. Here the y values are negative. So I'm going to make an assumption based on the pattern that I've seen that since the first point that I recognize on the graph is 1, negative 1 instead of 1, positive 1, that my a value is going to be negative 1, inferring that my equation might be y equals the absolute value of x times negative 1. Well, that's consistent with my pattern. That is, this line is the equation of this line is y equals negative x, decreasing line with a slope of negative 1. And if I remove the absolute value and leave the equation alone, I get y equals negative x. So this is consistent with everything we've seen before. So a equals negative 1 if negative 1 is the point that's paired with x equals 1. The second equation has the line the second line has an equation y equals x, which is what happens when we take the opposite of what's inside. The negative 1 times negative x equals positive x. Following the same pattern below, we find the point 1, negative 5 infers that the a equals negative 5, and that must be the equation of the absolute value, producing two rays, one with the negative slope, which results from leaving the absolute values out of the equation and doing nothing else, and the other as shown. Thank you for watching.